Good evening again, students. This video we're going to do Module 3, Topic 5, Proving Line Segment Relationships. Standard for this topic is GR 1.1 again. Prove relationships and theorems about lines and angles. Solve mathematical and real-world problems involving postulates, relationships, and theorems of lines and angles. The objective for this lesson is you guys are going to prove theorems about line segments. And the essential question is, what makes a logical argument, and how are logical arguments used in geometry? First, we got the bell ringer. We're on page 3 of week 6 packet. I'm going to pause for 3 seconds. Please work the bell ringer, and then unpause and see how you did. Alright, bell ringer. Proof. Complete the flow proof to prove that MN, line segment MN, is congruent to line segment PQ. They're also telling us that MN is equal to 5x minus 10, and that PQ is equal to 4x plus 10. Then MN equals 90. Drag statements and reasons to complete the proof. And I believe what they're asking us to prove is that MN is equal to 90. But anyway, let me keep going. Excuse me. Okay, so our first box here says given. Well, they gave us that MN is congruent to PQ. They also gave us MN is equal to 5x minus 10 and PQ is equal to 4x plus 10. So I'm going to put a little check mark there. And so this is all filling up this whole box. It would normally be that size, but obviously I can't write that small. But MN is congruent to PQ. MN is equal to 5x minus 10, and PQ is equal to 4x plus 10. Okay. All right, our next box says congruent segments have equal lengths, and then it says substitution property. So I believe this is actually putting in two answers. So congruent segments have this equal lengths. Well, if MN is congruent to PQ, then MN is equal to PQ, and then if we're going to substitute, we would substitute MN for 5x minus 10 and PQ for 4x plus 10. So that's going to be written in there like this. Equals PQ, and you're going to have 5x minus 10 equal to 4x plus 10. Okay, went over to the next box, pardon me. So let's check this one off. All right, next. We have x minus 10 equal to 10. So looks like they took and they subtracted 4x from both sides. That's how you've got 10 by itself over here, and that's how you've got x minus 10 over here. So subtraction. It's the subtraction property of equality. We're just going to shorten it down and put subtraction here because we have the word bank. All right, let's scoot up a little bit here and we can see the bottom of that. Alright, so our next box says addition property. Well, if we add 10 to both sides, we're going to have x equals 20. So there's that. Alright, and then the last one says substitution property of equality. If we plug in 20 for x, MN equals 5 times 20, which is 100, minus 10 equals, I'm just going to put it over here in the box, equals 90. So there you go. Alright, let's put some guided notes here at the bottom of the page. Let me recenter so I can get everything in here. Okay. When you use a ruler to measure the length of an object, you match the mark for 0 at one endpoint of the object, and then you look at the ruler mark that corresponds with the other endpoint. This illustrates the ruler postulate. Postulate 3.8 is the ruler postulate. The points on any line or line segment can be put into one-to-one correspondence with real numbers. The example says, given any 2 points, A and B are on a line. If A corresponds to 0, then B corresponds to a positive real number. And this is because when you're measuring length, you can't have a negative measurement. It can't be negative. It has to be positive. And of course, I'm not sitting in the classroom, so I don't have a ruler on me to put that in front of you. But if we put the ruler here, if we put the 0 there, we should end up like 3 to 4 inches somewhere right here. It'd be positive because it's a length, so it has to be a positive number. In this figure, point B is said to be between points A and C. You can also say that AB, let's make it say green, say AB plus BC, oops, plus BC, and of course equals AC. I'm just going to say A, drawing it underneath so we can see, but the green plus the orange equals the blue. Without a piece of string, it'd be the same thing. This is illustrating the segment addition postulate. Postulate 3.9, segment addition postulate. So if A, B, and C are collinear, like this, and B is between A and C, if and only if AB plus BC equals AC. Just like up here, AB plus BC equals AC. That's your segment addition postulate. Very important. We're going to have that in a lot of proofs and a lot of stuff. So please get that. If you need some help or you want to talk about it in class, please see me, send me a message. It's very important. Let's flip over to page 4. Centered up here. Okay, page 4. The I do is on the left, the you do is on the right. I'm going to try to put this where we can see everything, and that's kind of tough. Let me go back out one here. Hopefully you can still see well enough on the screen. Alright, so number 1, write a 2-column proof. They give us that QT is congruent to RV. So this is going to be kind of tough because these are on the same line. So so QT, so let's see, well, QT and RT. So basically from Q to T, R to T, we're not going to mark that. I do usually suggest marking your congruent segments, but when it's one line like that, it's kind of hard to do that. So let's look at this one. So number 1, QT is congruent to RV, and that was our given. They're wanting us to prove that QR is congruent to TV. So this little guy and this little guy are going to end up being congruent. So statement 2, QT is equal to RV. If you guys have been in class lately, you'll know that I have said till I'm blue in the face, not literally, that when we see a geometric figure, so QT, line segment QT is congruent to line segment RV, then QT is equal to RV. Anytime we have the same letters and we're going from congruent to equal or equal to congruent, it's always the definition of congruence. We do that a lot, and you see here there's 2 in the word bank, so there's 2 in this proof by itself. So it's important. Definition of congruence. And it's because, as I said, equals is for numbers, congruency is for shapes. But we're dealing with both at the same time, so we have to switch back and forth. All right, number 3. QR plus RT equals QT, and RT plus TV equals RV. So anytime we're talking about pieces of a line that equal the whole line, this piece plus this piece equals that piece. I say that a lot in class too. That's the segment addition postulate. And that's what this is. Alright, so number 4. QR plus RT equals RT plus TV. So QR plus RT equals RT plus TV. So we substituted QT and RV for that because they're equal to each other up here. So now we're substituting. We know that these two equal QT, so we can substitute those for QT. We know these two equal RV, so we can substitute those, and that's a substitution, and that's a given. You know, the book gave us those. All right, number 5. QR plus RT minus RT equals RT plus TV minus RT. All right, something we'll notice here. We have a minus RT and a minus RT. So we're subtracting that, and you see a plus RT, so these two are going to cancel, and these two are going to cancel. But this is a subtraction. That's all we're doing is giving the reason. This is because of the subtraction property of equality. That's just how I write it shorter. Alright, so that leaves us with QR equals TV. Page. And so between here and here we simplified, we combined like terms. RT's canceled, the RT's canceled. So this is simplification. Alright, then number 7 says is what we were trying to prove. Line segment QR is congruent to line segment TV. Again, equals congruent QR TV TV. Definition of congruence. I'm hoping if I stress this enough you guys will get it, and I think you will. Alright, so that's it for number 1. Number 2 is a you do, so please pause the video here, try to work this, follow what we did over here, and then unpause and see how you did. I'm going to wait 3 seconds. Alright, number 2, complete the 2-column proof. They give us that CE and FE, so it'll be tough with a crayon, are congruent, and ED and EG are congruent. So these two guys. Alright, so our first statement was just that, and it's given. As I said in the previous video, I think I said this in class, but if you mark these things, the congruent marks beforehand, it makes the proof easier. I didn't do it over here because it's all the same line and the marks kind of go together, but here we can see the green are congruent, the red are congruent. Alright, so line 2 here, and they give us this. CE is equal to FE. Definition of congruence. ED is equal to EG. Okay. Line 3. CE plus ED equals CD. So CE, the green part, plus ED, the red part, equals the whole line. Hopefully you said segment addition postulate. Because anytime we're talking about this part of the line plus this part of the line equals the whole line, that's what we're doing. All right, number 4, FE plus EG equals CD. So FE plus EG equals, hold on, did I get off here? FE plus EG equals CD. And the reason we substituted here, up here where CD, where did it go? Where did it go? Hold on. What am I doing? Oh, yeah, we're substituting CE and FE. See, they were up here congruent. So we substituted those, and then ED is congruent to EG, so we substituted that. Sorry, lost my train of thought for a second. So that's substitution. All right, now we have FE plus EG equals FG. So you see I got ahead of myself. I was trying to talk about that second segment addition postulate, and I got ahead of myself because I knew we had to talk about both lines. And you'll notice when we do these proofs, by the time it's over with, you've basically touched almost every part of the shape. So hopefully that helps. Number 6, CD is equal to FG. So FG right here, we know that CD is equal to FE plus EG, so we just substituted those here, or well, it's technically the transitive property, because if this guy plus this guy equals this one, and in most of these everything ends up being equal to everything else, at least in these examples. All right, number 7, CD is congruent to FG. So again, the equal sign, the congruent sign, this is the other definition of congruence. Hopefully this is starting to make a little more sense as we continue to practice. Alright, bottom of page 4. This portion here was a little out of place. We kind of talked about this earlier but didn't explain it. So you've learned that segment measures are reflexive, symmetric, and transitive. Because segments with the same measure are congruent, these properties can apply to segment congruence. So again, we're talking numbers versus shapes. But just like numbers, you could do this, you could do it with the shapes as well. So, theorem 3.2, properties of segment congruence. So we have line segment AB, line segment CD, and line segment EF. Reflexive says that AB is congruent to itself. And I mentioned this before, if we look in the mirror, we see our reflection. So when you see reflexive, it's going to be something congruent to itself. And I know right now well, why do we care if something's congruent to itself? Later on, when we get into triangles and we're starting to prove two triangles congruent to each other, when those two triangles share a common side, that common side is congruent to itself. You may not have understood a word I just said. I hope you did. But if not, we'll get into it later. So anyway, reflexive. When you see reflexive property, we are talking about something congruent to itself. Symmetric property. So if AB is congruent to CD, then CD is congruent to AB. Like if 1 plus 2 equals 3, 2 plus 1 also equals 3. And transitive is a little bit more complicated. So if AB is congruent to CD and CD is congruent to EF, then AB is congruent to EF. Hopefully seeing it like this makes a little more sense. So if this guy and this guy are congruent, and this guy and this guy are congruent, then these two have to be congruent. Hopefully that makes sense. All right, page 5. Number 3, the I do on the left. Write a 2-column proof. Excuse me. R is the midpoint of QS. Okay? So R is the midpoint of QS, so this guy and this guy are congruent. T is the midpoint of VS. So that means this guy and this guy are congruent. I just made the letters the same color just so we could hopefully see it better. They also tell us that QR is congruent to VT. Now I'm going to, I'm going to put 2 congruent marks away from the line. So QR and VT. And that's why I don't like doing 2 lines, the same thing here, but we need to know that this guy and this guy are congruent. So your greens are congruent, your reds are congruent, and then these blues are congruent. Notice the pattern. So if this guy and this guy are congruent, and this guy and this one, everything's going to be congruent. But that's how we learn how to do these proofs. So number 1, statement is R is the midpoint of QS and T is the midpoint of VS. And that is our given. All right, number 2 is QR is congruent to RS and VT is congruent to TS. Well, I've already marked these. So your greens are congruent, your reds are congruent. You look down here, we see midpoint theorem. And that's because if T is the midpoint, then VT and TS have to be congruent. If R is the midpoint, then QR and RS have to be congruent. Alright, number 3 says given, and this actually we had 3 given statements. There were the first 2, so here's the third, that QR is congruent to VT. Alright, number 4, they give us both the statement and the reason. QR is congruent to TS, and it's transitive. So, like if VT is congruent to TS and VT is congruent to QR, then QR is congruent to TS. Hopefully that you guys got that. So that was transitive. This should be an I here. Okay, number 5. RS is congruent to QR. This is also transitive. As I said, these are all going to be congruent to one another, and that's how we do it for learning purposes. All right, number 6 was totally blank. Well, we were trying to prove RS is congruent to TS, so we know that's the last thing we're going to have to say. And then the only thing left here is symmetric. And that's RS and QR and TS and yeah, it gets a little confusing even for the math teacher at this point. Alright, page 5. Number 4 is the you do. Please pause the video right here. I'm going to wait 3 seconds and then see how you did. Alright, number 4. Let's scoot over a little bit here. Complete the 2-column proof. Our given is B is the midpoint of AC. So B is the midpoint of AC. So I know both of those sides are congruent. C is the midpoint of DE. If you can't tell, that's 2 marks. Sorry, it's crayons. I can't help it. So C is the midpoint of DE. They also tell us that AB is equal to CE. So equal, not congruent. So I'm not going to put congruent marks. They want us to prove that BC is equal to DC. Alright, so number 1, B is the midpoint of AC, C is the midpoint of DE, given. Number 2, AB is congruent to BC, DC is congruent to CE. Definition of a midpoint. See, I already marked that. So I'm hoping you guys will get in that habit. Number 3, AB is equal to BC, DC is equal to CE. So we went from equal to congruent. So that's the definition of congruence. Hopefully, as we continue to practice, you guys will start getting ahead of me on these things. Okay. Alright, number 4 is another given. That's the AB equals CE right here. And then this last one is BC equals DC. And so they have substitution and prove, and actually either one work because we're proving that, but we're proving it because we're substituting. So DC equals, it actually would be transitive because DC equals CD and AB equals CE, then AB equals BC, BC equals CD. But we'll go with prove. Alright, bottom of page 5. Last guided notes here. Independent practice for this is available on McGraw-Hill. Let me finish up the notes here before I get ahead of myself. Okay, two-column proofs and flow proofs are considered formal proofs. A formal proof is a logical argument that includes all the steps and corresponding justifications needed to prove a relationship. An informal proof is a simplified proof that summarizes the logical reasoning used to prove a relationship. In an informal proof, some steps that are considered obvious may be skipped and some reasons or justifications may be omitted. That's going to be like the small stuff. The additions, the subtractions, we skip all that. We go from 4x equals blah 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 to x equals whatever. We skip that. And last, a narrative proof is a type of informal proof that can contain bullet points, lists, calculations, or paragraphs. So again, you guys, independent practice is on McGraw-Hill for this one, and we will see you in class. Have a good evening.